My name is Greg Peterson. I'm with Chadron State College, and I did my research on the determination of heavy metal species in reservoir sediments of the Pine Ridge and Black Hills region of Nebraska and South Dakota. So lake sediment buildup occurs from runoff through surrounding geological structures and inflow from the stream. So the geology of the region really has an impact on what type of sediment we see in these reservoirs. The metal content of the sediment is also important because at high levels it can pose a risk to the environment and the surrounding wildlife. However, how the metals are actually chemically bound to the sediment plays a large role in the availability and mobility of that metal and onto how it can actually affect the environment. And I will get more into the chemistry later as I go on and discuss the methods that I chose to follow. So my research question was, how do the various contributing factors affect sediment metal accumulation in Box Butte, the Chadron Dams, Whitney, and Angostura reservoirs? So this was my study area. Up here is South Dakota. Angostura was the only reservoir in South Dakota. Down here we have Whitney, the Chadron Dams, and Box Butte, which are all located in Nebraska. Angostura lies kind of in the foothills of the Black Hills. Whitney is in between the Black Hills and the Pine Ridge. The Chadron Dams lie within the Pine Ridge, and then Box Butte lies up above the Pine Ridge. So Angostura receives water from the Cheyenne River. Whitney Reservoir receives water from an aqueduct off of the White River. The Chadron Dams are supplied by Chadron Creek, and Box Butte is supplied by the Niobrara. So both the Niobrara that fills Box Butte and the Cheyenne River that fills Angostura flow out of Wyoming and into these reservoirs, whereas Whitney and the Chadron Dams, both of the creeks that fill these reservoirs, are spring-fed within the state of Nebraska. I would also like to point out that Angostura, Whitney, and Box Butte were all originally created for irrigational purposes and kind of double as recreational areas. The Chadron Dams, however, supply, or part of the supply, to the town of Chadron's drinking water. Looking at the geology of each of these reservoirs, this matters because the different formations that the water flows through and the reservoirs sit in will have an effect on the type of metals that we expect to see within those reservoirs. So working from the bottom, which lies in the oldest rock, to the top, which lies in the youngest formations, Angostura it flows through Pierre Shale. The reservoir itself sits in Belfuge and Carlisle Shale. A little bit younger, we have Whitney Reservoir, which lies in Pierre Shale, and the White River flows through the White River group. The Chadron Dams primarily are affected by Rickery, and then Box Butte Reservoir flows through Ogallala, and then the reservoir itself sits in the Rickery Formation. Moving on to my methodology, to collect samples, I went out on each of these reservoirs in a kayak. I used a dredge, which you can see pictured here. I used the dredge to collect the samples. You drop it off the side of the boat, it grabs the sediment, bring it up, and empty it into a bag where I took the GPS locations of it. At each location, I took 2 samples. I also made sure to wear gloves and change these gloves between each sample to avoid contamination, as well as rinsing the dredge off really well, is to make sure that no sediment was transferred between sample sites. I collected a total of 31 samples. I based the number of samples per reservoir roughly based off of the size of those lakes. So the Chadron Dams, which were the smallest, had the fewest samples, whereas Angostura, which is the largest reservoir, had the most samples. After all of my samples were collected, I brought them back to the lab and dried them in an electric oven at 150 degrees Celsius. It was then ground with a mortar and pestle by hand and sieved to a grain size of less than 53 micrometers. I went to less than 53 micrometers because this gets us down into the sands and silts and gives us the best surface area to volume ratio, so that it gives us the best picture of what metals are actually present in the sediment of these reservoirs. Moving on to the extraction process, I chose to follow a 4-step sequential extraction rather than just a 1-step extraction, because it gives us an idea of how the metals are actually chemically bound to the sediment. How the metals are chemically bound really matters because some of those may be very available to dissolve into the water and affect the environment, whereas others may be less available, and even though they're there, they may never actually be freed to have any kind of effect on the environment. So looking at fraction 1 of this extraction process, it looks only at metals that are exchangeable and those bound to carbonates. Moving on to fraction 2, this looks only at reducible metals and those bound to iron and manganese oxides. Fraction 3 looks at oxidizable or metals that are bound to organic substances. So up through fraction 3 is really what we might be able to see in the environment, with fraction 1 being the most available of those first 3 fractions. But when we look at fraction 4, this is only testing for residual metals, anything that's left over in the sediment. So we will never see environmental conditions that replicate what this 4th fraction did to extract the metals. However, it is an important step in determining the total metal content of each of the samples. So to give you a little bit better idea of what this looked like in the lab, I took 0.8 grams of my sediment, starting up here with fraction 1, put it in a beaker with a stir rod in 0.1 molar acidic acid, and stirred for 16 hours at 50 degrees Celsius. This is just looking at carbonates. So I then take the sample, centrifuge it, collect the liquid phase, and move only the sediment on to the next fraction. So the second fraction is looking at reducible metals. So I used 0.1 molar hydroxyl ammonium chloride at a pH of 2, where it was stirred again for 16 hours at 50 degrees Celsius on a hot plate. This was again centrifuged, collected the liquid phase, and moved only the sediment onto fraction 3. Because we're looking at oxidation in this phase, I used 2 treatments of 30% hydrogen peroxide, which I evaporated in an electric oven, and then introduced to 1 molar ammonium acetate at a pH of 2. The ammonium acetate in this case is just to make sure that anything that was oxidized stays in solution and doesn't reabsorb to those sediment particles. We want to keep everything in solution so that it can be analyzed and don't want anything to reattach to the sediment. Again, this was stirred for 16 hours at 50 degrees Celsius, centrifuged, and moved on to fraction 4. Fraction 4 used aqua regia, which is a 3-to-1 molar ratio of hydrochloric acid to nitric acid. This was evaporated at 150 degrees Celsius and then filtered again so we could look at the extract. Each of the extracts was then diluted to 50 milliliters and put through ICP-MS analysis. ICP-MS stands for Inductively Coupled Plasma Mass Spectrometry. I was fortunate enough to go down to the University of Nebraska, Omaha, where I met up with Dr. Rich DeRager, and he helped me to use this machine. So right here is the auto sampler, so I put each of my samples in these test trays. It automatically takes a sample, injects it into the machine, vaporizes it, and then the plasma ionizes it to a positive charge. The spectrometer then uses alternating voltages to allow very specific mass to charge ratios through it at a time. So what this allows us to do is analyze for one element at a time, which is then accurate down to 1 part per billion. Moving on to my results. So I chose to organize my data with total metal content at top, and then each bar graph is divided into each of the 4 fractions. So I obtained the total metal content by adding together each of the fractions that I got from one sample and then averaging that total across all other reservoirs. And then I did the same thing. I averaged each of the fractions as well. So if we look at Whitney here, you can see it has blue, which represents the fraction 1, orange is fraction 2, gray is fraction 3, and then finally fraction 4 at the top here. So this is basically the kind of graphs that I expected to see for the majority of metals that I analyzed for. This is because Whitney and Angostura we would expect to have higher metal levels because they sit in black shale, and black shale is formed from marine deposits that then undergo oxidative processes that really end up in metal kind of being concentrated in that black shale. So it would make sense that those would have higher metal content versus box butte and Chadron dams. So in the case of lead, we see that it fits this prediction. Whitney and Angostura are significantly higher than the Chadron dams and box butte. While Whitney is up to 11 parts per million, this is not necessarily something to be of concern, especially when we look at through the fractional process. Little was extracted in fraction 1, and a significant amount was extracted in the 4th fraction, so not overly available to the environment. Box butte in this instance was a little higher in lead content than I anticipated, and I'm guessing this is likely because of the sandstone within the Ogallala group that it sits in. Sandstone is known to contain lead, so that might be the cause of the lead that we're seeing in box butte. Moving on to arsenic. Whitney clearly has the highest levels here. I want to first preface this with saying that we're still in parts per million, but the scale did change here significantly. So arsenic is common in the black shale again, so that would explain the levels we're seeing in Whitney and Angostura. But then we look at box butte and the Chadron dams, and we're seeing very similar levels to that of Angostura. And this is not what we expected for arsenic. We don't really know where this would be coming from, but it's not necessarily of concern. However, when you look at the Chadron dams, the blue here represents the 1st fraction, which is the most readily available to the environment. That is arsenic that's bound to carbonate or exchangeable with the water. So in this case, we have almost 1.5 parts per million of arsenic that may be available to enter our water supply. However, the city does check for arsenic and they report that it is below dangerous levels. Moving on to selenium content, you can see here again that Whitney and Angostura, which lie in the black shale, have quite a bit lower levels than box butte and the Chadron dams. We're still in parts per million here, but the Chadron dams had the most total metal content at 1.7 parts per million, whereas Whitney and Angostura were significantly lower than both of these. Another interesting note about selenium is that this was one of the only metals that I saw primarily extracted in fraction 3, which again is represented by the gray here. You can see that across every reservoir, this metal was extracted in the 3rd fraction, which is oxidation. So for whatever reason, selenium is primarily freed through oxidative processes, and that was just an interesting observation I noticed as I was sorting through my data. Finally, looking at uranium. Uranium showed some interesting things in that it was not where we expected it to be at all. The Chadron dams, which again are the city's drinking supply, have up to 6 parts per million of uranium for total metal content, and most of this is extracted through the first 3 fractions, which means that it is potentially environmentally available. Very little was actually extracted in the 4th fraction here. Also, if you look just at fraction 1, which again is bound to carbonates and exchangeable metals, we have almost 2 parts per million there. So I think this could potentially be of concern. You can't really say without future studies. It's also interesting to know that it does not appear that our drinking supply is monitored for uranium. So this is definitely something we want to look into in the future. One theory that I initially thought might help explain this uranium content was the fact that it sits in the Greggory Formation, and parts of the Greggory have been shown to contain high levels of lignite, which contains uranium, but in this region lignite is pretty much absent. We would have expected Whitney to show the highest level of uranium because it sits right above the Chamberlain Pass Formation, which is known to contain a lot of uranium, but obviously it does not contain near the levels. So in conclusion, Box Butte and the Chadron Dam showed higher levels of trace metals than we expected to see, and don't really know why this is, and definitely something we want to look into more in the future. Maybe of more concern, the uranium content of the Chadron dams is surprisingly high, with a high level in the first fraction. So again, this is the fraction that is most available to the environment. So I really would like to know why that is, and are we actually seeing this enter the water and the drinking supply of the town. Finally, the results of this will help establish baseline information for the students that plan to follow up this research. So for future research, I would like to skip directly to the fourth fraction so that I can analyze total metal content without taking it through the sequential extraction procedure. And this would just be to verify that nothing is lost through this sequential extraction. I would also like to test the water for iron, manganese, and nitrates, because iron and manganese have been shown to pull metals like arsenic into solution. They actually make them dissolve easier into water. So if those things are present, it may affect what is entering the water. Nitrates can act as an oxidizer or an oxidation agent and bring things like uranium into solution as well. I would also like to test stream sediment and water in an upstream progression from each of these reservoirs to see if it stays consistent or changes as we move upstream. And then finally, I want to know what's causing the trace elements that we see in Chadron dams, and particularly uranium. I would like to thank Chadron State College for allowing me to use their research facilities, and a special thank you to Dr. Richter Egger and the University of Nebraska Omaha for letting me use the ICP-MS machine and helping me to understand and organize that data. Here are my sources, and thank you for watching my presentation.